Would we hop between various aspects, like jumping on a train to go from one state to the next? Do you think of every decision that you make perhaps significantly altering the world that you exist in? It isn't so much that your decisions make unique universes. Various universes get made, and perhaps you're different in them. Well, the idea of various aspects existing probably won't be fictitious. After all, CERN has quite recently made a stunning revelation about the chance of opening an entryway to another aspect. What will this mean for us? Is it even feasible? In particular, are there any results to intruding with the texture of existence? Go along with us as we jump into CERN's creepy yet intriguing research. The job of CERN is to get to the lower part of the entire arrangement with gateways, aspects, and particles. We first need to comprehend what CERN is and what it does. CERN, otherwise called the European Organization for Nuclear Research, is the result of scientific imagination, settled in the core of Europe. This research office has been in the beautiful wide open between the French and Swiss borders since the 1950s. Delegates from 12 European countries assembled in Paris to lay CERN's foundation in light of one objective: making a center for nuclear research that would drive Europe to the very front of scientific revelation. Over the years, CERN has made significant contributions to the world, specifically the World Wide Web in 1989 and the Large Hadron Collider (LHC) in 2008. The LHC was the world's most powerful particle accelerator yet, buried far below the Earth, crossing more than 17 miles in circuit with gear, for example, magnets, sensors, and experimental devices. Inside the heart of CERN is to assist us in understanding the universe around us exhaustively, and they do this by looking at the smallest constituents of the universe, particles, with a variety of particle accelerators and other apparatus available to them. They plan to dive deep into fundamental physics. One such piece of equipment is the Large Hadron Collider, as previously referenced, which is relevant to the subject of various aspects yet to be investigated. The Large Hadron Collider and the particle collision process. So what is the Large Hadron Collider? Well, the LHC is the world's largest and most powerful particle collider. This feat of engineering is so astounding because it was built by the efforts of over 10,000 scientists and many universities as well as research centers. It is hidden from sight at a depth of 175 meters, 574 feet, below the Earth's surface and lies in a 27 kilometers tunnel near Geneva. The first collisions from the LHC were achieved at an energy of 3.5 tera-electron-volts, TeV per beam in 2010. This amount of energy was significant since it was multiple times the previous world record. However, the LHC has been shut down numerous times for repairs and upgrades, particularly between 2013 and 2015 and later in 2018, after which it was reopened in April 2022. These regular closures resulted in the upgrade of the LHC from 3.5 TeV to 6.5 TeV per beam, maintaining its status as a powerful atom smasher and collider. 9 detectors and 4 intersection points allow the LHC to perform at the top of its game, detecting various phenomena around the intersection points. Anyway, why are they even doing this? What need do we have to collide particles? Well, the objective is to find solutions to different inquiries. Where are the families of new particles anticipated by supersymmetric theories? What do the particles do when they slam into one another at various rates? What about the speed of light? Imagine if there are new particles whose presence we are completely ignorant about. All these unresolved questions in particle physics are the reason why we built an organization as enormous as CERN. That brings us to the intriguing process of particle collision, something that has brought us endlessly closer to the possibility of different aspects. The process of particle collision is arguably the most straightforward methodology for studying the most fundamental pieces of our universe. In basic terms, we use such enormous machines to smash things together and see what happens. A very Neanderthal approach to be sure, but it works. Anyway, what separates us from Neanderthals is our devices and our approach. Rather than rocks and bones, we have accelerators that can make particle speeds approach the speed of light. In this multi-step process, the LHC comprises radio frequencies that speed up charged particles to almost the speed of light. They have superconducting magnets to maintain the circular path of these particles as their speed strongly approaches 0.99999 times the speed of light, just 3 meters/second short of being the actual speed of light. The absolute initial step is to inject the particles into something called a linear accelerator or LINAC. What it does is charge the particles to reach speeds of roughly 50 million electron volts. Then they are injected into the circular accelerators, which slowly increase the energy of the particles to a few trillion electron volts. Some of these circular accelerators include the proton synchrotron booster, the proton synchrotron, and the superproton synchrotron. Finally, the two main rings of the LHC, 27 kilometers in perimeter and 71.31 Tesla magnetic fields, accelerate the particles up to 7 TeV, and then the particles collide head-on from opposite directions. These high-energy collisions result in us observing some interesting things about the particles, whether it is new particles being formed or an impact of energy being released. These observations help us get closer to understanding the universe around us. These collisions produce a wide array of particles, some that have never been seen before by any laboratory. How are these small particles detected? The detectors, placed in various locations inside the collider, track the paths of the charged particles and measure their energies. Examining these particle creation patterns allows us to determine the properties of the detected particles and provide further objective facts about their behavior. An inquiry might arise in your mind. How do the particles in the LHC not miss each other during this particle collision process with a size so small? How do they move with such precision? Upon closer observation, it is noted that the particles in the LHC are packed into needle-like bunches and then compressed to reach the collision point. Each needle-like bunch is said to contain around 1, 0, 11, 10, 11 protons, with just a handful of collisions each time the two bunches collide. Due to the continuous collisions, they can amount to billions every day. Anyway, as impressive as this creation is, there have been quite a few concerns about the LHC since it was built. Concerns about the Large Hadron Collider have been around for a long time, nearly since the inception of the facility. Since its early stages, concerns about accidentally creating a black hole were raised, estimating that it could consume our world. Recent revelations by the Large Hadron Collider have not halted the clock of development and investigation, leading it to discover some astonishing things. For instance, physicists identified a mysterious primordial particle known as the X particle in mid-2022. More specifically, it was X3872, first discovered in 2003 by the Japan-based Bell experiment. In this experiment, the particle collider smashed together high-energy electrons and positrons to form the elusive X particle. Yet, they ended up decaying too quickly for any detailed study. It was then suggested that X3872 would be better elucidated in a quark-gluon plasma. By 2022, around 100 of these X particles were detected within a sample of quark-gluon plasma by smashing together lead particles. These particles were estimated to exist close to the Big Bang for a very brief period. These discoveries were published on January 19 in the journal Physical Review Letters. Did you know that what we find in space, like PLA, planets, stars, and galaxies, is only a small piece of the entire picture? In fact, it amounts to just around 4% of what's out there. What truly defines the universe isn't so much the things we can see, but the empty space around them. Researchers have found that most of the universe is made up of things we can't see directly. These invisible substances don't emit light or any other form of radiation that telescopes can detect. Instead, we can detect them due to the way they influence the movement of stars and galaxies through gravity. We call these mysterious substances dark matter and dark energy. We're still not sure exactly what they are or how they've shaped the universe. However, they open up intriguing possibilities for discoveries in physics. Dark matter makes up around 23% of the universe. We first thought of its existence back in 1933 when we observed that the way galaxies move suggested there was more stuff out there than we could see. We can't directly see or interact with dark matter, but there are methods for getting around this issue. Dark matter can be described as a thief leaving a crime scene. The physicists survey the crime scene for dreadful steps, and these imprints give us clues and signs about how much of it is out there. So why might dark matter be made of one thing? One thought is that it may be made of supersymmetric particles. These particles are like secret partners to the particles we already know about. Even so, researchers are attempting to find these particles in experiments like those occurring at the Large Hadron Collider. Now let's discuss dark energy. Dark energy makes up around 73% of the universe, making it one of the most significant characters in the grand stage. Dark energy seems to be responsible for an astonishing observation made in the 1990s. The expansion of the universe is accelerating. This was a major shock since researchers had thought the universe's expansion would slow down over time due to gravity. Instead, it appears as though something is pushing the universe apart. Researchers have called this mysterious force dark energy. They think it might be related to a force called the cosmological constant, which Albert Einstein once proposed could exist. One of the ways researchers study dark energy is by looking at how galaxies are spread out across the universe. They examine the light from supernovae, which are exploding stars. Supernovae are so bright that they can be seen from very far away, and they serve as cosmic landmarks. By measuring how the light from supernovae is stretched over time, researchers can figure out how fast the universe has been expanding. Another thought is that dark energy may be a new kind of energy field that fills space. We still don't fully understand what dark energy is, but studying it could help us comprehend the fate of the universe. Will the universe continue to expand forever, or will it eventually stop? Dark energy holds the key to this cosmic mystery. So how does CERN come into play? It turns out CERN has been noticing some abnormal behavior in neutrons, one of the building blocks of atoms. In specific experiments, neutrons appear to be vanishing and reappearing like magic. Yet, researchers think there may be a scientific explanation. The neutrons may be slipping into an alternate universe. This idea is based on a hypothesis that our universe may be just one of many, like bubbles in a vast bubble bath. If this is true, there could be other aspects out there that we can't see. Researchers at CERN are now planning experiments to test this idea. They're trying to create conditions where neutrons could slip into another aspect. If they succeed, it would be a huge breakthrough in our understanding of the universe. If CERN truly can open a doorway to another aspect, it would change everything we know about science. It could help us understand dark matter, dark energy, and the very nature of reality. This discovery would be like finding a hidden doorway to another world full of possibilities and new knowledge. We might discover new particles, new forces of nature, or even new ways to travel through reality. CERN's mission to unlock the mysteries of the universe by potentially opening a gateway to another aspect is a monumental endeavor. This journey into the unknown promises to unravel the mysteries of dark matter and dark energy and redefine our understanding of reality. The implications of such a discovery are vast, offering a glimpse into